just let them know one more minute.
Good morning, everyone. We're going to begin in just a minute. Please stay with us. Welcome, everyone. Welcome to Drones for Surveying, Viability, Versatility, and Vision, and thank you for joining us this morning. My name is Marty Nesher, President of the Business Journal News Network. This webinar is being presented by the Business Journal News Network and Microdrones. Some quick housekeeping before we begin. If you have questions during this presentation, please type them into the chat function at any time, and our presenters will answer them at the end. Please let me introduce one of our presenters today, Chuck Dorgan. Chuck joined Microdrones in April 2016 as the Sales Director for the United States. He brings a wealth of sales and engineering experience to the company, having spent more than 16 years in management positions at United Technologies Corporation and nearly 7 years at Xerox. Chuck earned his MBA from Le Moyne College. Now let me turn it over to Chuck.
Thank you, Marnie. Thank you very much for the Business Journal Network and Visual Technologies for putting this on for us today. I'm Chuck Dorgan. I'll talk a little bit about Microdrones first. Microdrones introduced the first commercial quadcopter in 2005. Based out of Siegen, Germany, Microdrones has been producing industry-leading rugged frames that are resistant to wind and harsh weather. Over 1,000 customers and businesses worldwide trust Microdrones. Microdrone's industry-leading airframe is known for being able to handle whatever Mother Nature can dish out. Our airframe is built with carbon fiber covered with high-end automotive paint. Microdrones can fly up in the rain up to 45-degree angles, withstand dust particles down to 1 millimeter, and operate in temperatures ranging from 14 to 100 degrees Fahrenheit. Our airframe flies in a plus-shaped formation, which is different than the traditional X formation. This plus formation gives us the efficiency and stable flight. The motors are run at a lower RPM, at 2,500 RPMs actually. This gives us the ability to go with about 10,000 flight hours before needing any maintenance. Our operating system and autopilot were designed and built and continuously improved by Microdrones. Here are our three airframes here. Starting from the left, the MD4-200 was introduced in 2005. This introductory airframe can lift 250 grams for 20 to 25 minutes. The MD4-1000 was introduced in 2009. To date, our best-selling platform, it can lift 1.2 kilograms for 30 to 45 minutes, depending on weather conditions. And then last but not least, the MD4-3000, which was introduced earlier this year in January of 2017, the heavy lifter, as we call it. The payload capacity is 5 kilograms up to 45 minutes. All of our frames remind me of the Boeing 747. That airplane was in service for 40 years, but they continuously improved on it. And that's the same thing that Microdrones does. We've had customers that have owned MD4-1000 for 7 to 8 years ago, and they've been able to easily upgrade the technology on the inside to match what's going out the door today. Oops, sorry. So on the left, basically you see a drone. On the right is a complete solution. And this is where we strive. We thrive in building the best airframes and building the best complete solutions for our customer. So basically it's the best airframe out there in the market with the best sensors we can find, with the software developed by Microdrones, by the people that work at Microdrones, equals the best results in the field. Speaking of solutions, here are our three main mapping solutions. On the left is our MD4-200, MD Mapper 200, getting started with a smaller, easy to transport system for your toolkit. The second one's the MD Mapper 1000, offering longer flight times and higher resolution sensor. And then our, last but not least, our flagship model, the MD Mapper 1000 DG, which offers survey-grade results without setting up time-consuming ground control points. And this kind of gives you an idea of the time savings based compared to like traditional surveying. Time is money, and as you can see with our packages, you can probably cut your traditional times down to like 20 to 30%. So what takes you weeks and months now takes you days to do. I want to turn things over to Dr. Mustafa, who is our Director of MD Solutions, which is Microdrone's new product development group. Dr. Mustafa has a PhD in geomatics engineering from the University of Calgary and has more than 18 years of experience in system design, development, integration, calibration, and quality control. Now to you, Dr. Mohammed.
Thank you, Chuck. Good morning, everyone. As Chuck mentioned, we offer solutions, and a solution contains a drone as well as the payload that consists of either cameras or scanners, as well as the georeferencing technology of inertial GNSS integrated solutions. I would like to define georeferencing in photogrammetry. The word georeferencing is simply some means of referencing an image taken up in the air with respect to the ground, or in more precise terms, with respect to a mapping frame of reference on the ground. And georeferencing could be either done using a traditional technique such as area triangulation, or the more modern technique called shape from motion, or done with our technology called direct georeferencing. The old technique, we establish and survey ground control points, then measure them, and then do the computations in order to produce mapping products. While the direct georeferencing technology, we measure everything up in the air using our APX system that contains GNSS and inertial technology. We georeference the image up in the air while the drone is flying. And from those measurements, we go through a little bit of quality control to produce the final mapping products without any need for ground control points. There is math and science behind direct georeferencing. The good news is that we already figured all of that out, and it's already implemented in our hardware/software/firmware, and this is all done perfectly well as part of our solutions. For those of you who are interested in learning more about the technical details in here, please feel free to contact me, and I will be glad to guide you through the mathematical background for that. One of the activities that we regularly do is thorough research and development in order to produce the final mapping product accuracy assessment results and share that with the public so that everyone knows the technical specifications of our solutions. What we're looking at here is a group of flight tests. We've done 10 of those back in the fall of last year using the MD Mapper 1000 DG. A number of cameras were involved. The Trimble APX-15 was involved, and we flew 60 meters above ground, 120 meters above ground, and we established 14 ground control points for accuracy assessment purposes, and that was done in Montreal in Canada. The starting point of any of the accuracy assessment projects is a base station. And for that, we actually established our base station using multiple sessions of 12 hours at a minimum over a few days in a row. And we processed the data using different software technologies, including the Canadian Spatial Reference Station service, which uses the precise point positioning technology. And we ended up with the accuracies that you can see in the table here. Excuse me. And those are 2 millimeters, 3 millimeters, and 9 millimeters in X, Y, and Z, respectively. Those are not the standard accuracy that we end up with using GPS for survey purposes. Those are geodetic accuracies that national government organizations end up achieving when they do what we have done in here for their first order class 1 geodetic network stations. And the purpose of us doing so is to establish a very high precision and a very high absolute accuracy base station for all of the flight accuracy assessment analysis. In order to assess the accuracy of the systems that we done the testing for, we established 14 control points, and as you can see from the upper left corner picture, the distance between the base station and the ground control points ranged about 1 kilometer, which is really small. And the distribution from the next picture to the right, the distribution of the ground control points is very, very well. The lower left corner picture here shows the way the ground control points show up in the images. You can tell that they're crisp and clear. And the next few plots here are showing the accuracies of what we achieved in the ground control points. So what matters to us is not the actual number of the accuracy. What matters is that the ground control point accuracy is higher than the ground sample distance, which is the pixel footprint on the ground. So in our case here, we flew at 60 meters above ground, which resulted in 0.8 centimeter GSD. And the ground control point accuracy there is very consistent with that. And for the higher altitude flight, the 1.6 centimeter ground sample distance, we have a very much higher ground control point accuracy. So that way our reference, the ground control points that we use to assess our system accuracy, is higher than the image ground sample distance. This is the pattern of the flight. We ended up with 891 processing configurations to analyze the advantage of DG over the old technology and look at different structures of image blocks or strips for corridor mapping, because that's a very important keyword here if we're doing corridor mapping beyond line of sight. And as well, we assess the orthomosaic accuracy and elevation or surface model accuracy. That spreadsheet is just an example of how we assess the accuracy by locking all of the parameters in the equation and only check one parameter at a time. And that's a standard way of operation when it comes to R&D or research and development, to learn about different parameters in that mathematical formula. The next few slides, I will be addressing the accuracy assessment results. The first one here is displaying the roll, pitch, and heading of the drone while it's flying. The upper plot is the roll. You can tell that the roll angle is very smooth. And the second one is the pitch. And then the third one is the heading. During the flight line, the angles are very smooth, and that's one of the advantages of the drone. The next slide is showing the residuals of GPS and GLONASS. Now, our GNSS solution includes both GPS and GLONASS. The residuals of GPS are basically usually better than the residuals of GLONASS. GLONASS is noisier, but yet it provides more satellites, so it adds more strength to the solution. And what we're looking at here is very smooth residuals within a centimeter for GPS and within 2 centimeters for GLONASS, and that's an actual absolute accuracy residuals, which is excellent. Now this slide shows the accuracy assessment results of the ground positioning accuracy, absolute accuracy of targets on the ground, and those targets are basically the unused ground control points. We call them checkpoints. And when you look at those repeated blocks of bars, the first one is saying number 1, then number 2, number 3. This is one flight called flight 2 amongst the 10 flights. The first group of bars represents one block of that flight, which is about 4 strips, 30 images each. And it shows the white bar is the X accuracy, the gray bar is the Y accuracy, and the black bar is the Z accuracy. And we can tell in block number 1 that we're looking at 2 centimeters in XY and about 3 to 4 centimeters in Z. And then block number 2 is another 4 strips of 30 images each, and then block number 3 and 4 and so on and so forth up until block number 7. So we basically dissected flight number 2 into 7 different blocks, and we looked at the accuracies accordingly. The curve on top of those blocks is basically the number of checkpoints involved in each block of those. What we can tell from the plots that we had in the past slide of 4 strips, that the accuracies are very repeatable and consistent amongst the different blocks. So as in this slide, which shows 3 strips only, and the next slide is actually showing 2 strips. So we have 6 blocks of 2 strips each. The reason we have 2 strips is that in the corridor mapping business, which is flying over a road or a railroad track to map an infrastructure project, we end up with long strips of data, and we typically do 2 strips for redundancy purposes, and a DG system is the only system in the world that could actually handle long and narrow strips of photography without building an area of images. We are actually handling long and narrow structure of the block of images because of the strength of the DG, which is having the angles involved in the measurements. And again, we're looking here at very repeatable accuracy for the 6 different blocks in flight number 2. And we, across the different flights, which is like 10 flights, we ended up with consistently and repeatable same level of accuracy. Now, we actually wanted to address the lens distortions because we are using commercial off-the-shelf components. So we analyzed a number of lens distortion profiles for different lenses on our cameras, and as you can see from those plots, they're all within 5 microns on the left-hand side up until an area which is we call the sweet spot in the image. After that area, we are actually at the level of the corners of the image. We have a little bit of differences in the lens distortion, and that's basically the finding that we came across, which allows us to do orthomosaics in the sweet spot. And the good news is that that's what we do with the orthomosaics. We actually produce the orthomosaics in the sweet spot only. But now we cannot actually produce stereoscopic mapping like the good old days when we used to fly manned aircrafts. So we have a limitation in the stereoscopic mapping. We cannot actually produce stereoscopic maps now, but nobody does. And we haven't actually received so far any request to do stereoscopic mapping because of the complexity of the equipment involved and the necessary skill set of personnel that need to be involved to produce stereoscopic maps. So we haven't come across any request to do so, and we are currently not really capable of producing stereoscopic maps, but this is one of the topics that we have on our to-do list for research and development. In conclusion, we repeatedly and consistently came to or achieved the accuracy of 2 to 3 pixels in easting and northing and 4 to 5 pixels in height, using either 4 strips of data, 3 strips of data, or 2 strips of data, which implies we can actually do both area mapping, an area of a square or a rectangle, a nature, or a corridor mapping, a rectangular shaped long corridor of roads or high tension power lines, and so on and so forth. And flight calibration needs to be addressed, as I just mentioned in the past slide, to address some aspects such as stereoscopic mapping at the far edge or the corners of the images. This is a real-world project done up in Quebec in Canada in an area called the Frere Dam. That dam actually is a very difficult to occupy with the typical land survey equipment and technologies and personnel. And we needed to do a survey of that dam. And we ended up doing it, as I mentioned, with the corridor mapping. You have that strength of the system because it collects the GPS data on board the drone as well as the inertial data, so you have the angles up in the air. So we did 2 flight lines, 12-minute flight time, 14 km/h platform speed, and we only used 5 checkpoints at the far ends of the dam, basically on land, not on the dam itself, because it was not permitted to establish any control or checkpoints on the dam itself. This is the orthophoto mosaic that was actually produced 5 hours later after we landed. and the accuracies are actually shown in that slide at the bottom. I apologize for the size of the table. It's kind of a little prohibiting to read, but I will read the numbers for you. Basically, what we're talking about here is that we analyze the orthophoto mosaic accuracy in both X and Y. And what we're looking at here in the number of RMS is 3.3 centimeters in the easting and 1.5 centimeters in the northing. And that accuracy is actually equivalent or similar to the nature of accuracy that we end up with in the land survey techniques, especially for a long and narrow traverse like what we would have established on a dam of that nature. So the advantage here is that everything was done in the same morning, data planning, mission planning, data preparation, and data acquisition, and then data processing in the same morning, and we ended up with that kind of level of product, a visual true orthophoto, together with accuracies that match the current technologies in the land survey industry.
Thank you, Mohammed. So that was the first or the second of a couple real-world examples. Another one here is Juniper Flats Basin Survey. The challenge here was with the question they were asking, is this reservoir built to specification? And will it hold what it's supposed to and keep the people and the property safe around it? So this is a project that we came in and used our MD Mapper 1000 DG, that's direct georeferencing, and we installed the ground control points for to use as checkpoints.
In order to do the survey, we actually flew 120 meters above ground at a 6 meter per second speed, and we ended up with 72 images covering the entire area, with a ground sample distance, which is the pixel footprint on the ground, of 1.8 centimeters, which is equivalent to 0.7 inch, and the entire flight time was 8 minutes.
So the supervising land surveyor, Joshua Tremba, quoted, after we've finished this project, the cut-fill models allow us to identify areas that were not built to spec. For instance, the south access roads really stand out because they were field engineered to be wider than the original plan. Also, debris and sediment removal. We could produce quick maps and show exactly how much dirt needs to be removed in any given location. This is really good visual supplement to the traditional earthwork volumes. So check the accuracy. Go ahead.
Although the DG system doesn't require ground control points in the processing workflow, but we typically like to make sure that we put the map on the right spot. So we do our own accuracy assessment for each project, and that is typically accomplished by having some corner checkpoints and some central checkpoints in the area we're flying, and that's what we've done here in this project. And we ended up with the accuracies listed on that table. At the bottom row, it says RMS, which is root mean square error. In meters, it's 1 centimeter, 2 centimeter in easting and northing, and 5 centimeters in Z, respectively.
Okay, so now we'll get to the next section here, versatility. Let's start out with versatility for your business. There's several points there. Our system gives you versatility whether it's mapping in the morning or inspection work in the afternoon. It saves time to get more done, improves worker safety, and takes away parts of the job that are dangerous, dull, and dirty. To be more competitive, people are asking for drone surveys because it's becoming a standard, up-to-date work. Collect data without shutting down regular groundwork, i.e. volume calculations and open mines is a classic example of that. For surveyors on the call, with DG you can slash your post-processing times and eliminate the need for ground control points, as Mohammed has been discussing. So we're going to get into some of our payloads, and what really gets some of the power of the microdrones airframe is we don't just build a system with a sensor integrated in it, and that's what you use. And if you want to do something different, you have to go buy another drone. Our drone could be used for many different things. So when you purchase a mapping package from Microdrones, you have the ability to expand the usefulness of your drone. Keep your options open with multispectral imaging, thermal imaging, aerial inspection, and soon to come out LiDAR. To start off with, probably our most popular add-on we offer today is the Plus I. That stands for inspection. You can turn your MD Mapper 1000 into a powerful aerial inspection tool with the Plus I add-on. The system makes it easy to collect the data and to create accurate three-dimensional models. So with the Plus I, you can take images of structures from various angles. You can view the camera. You can see exactly what the camera's looking at with a 7-inch LCD monitor. Make sure you're capturing what you want to capture. You can frame in images, obviously, with that monitor. And whether you're completing infrastructure inspections, planning engineering work, or survey construction sites, Plus I adds the flexibility to your UAV system. Another very popular payload is the Plus T. That stands for thermal mapping. Our Plus T package, thermal mapping add-on, this package comes with custom-built nadir mount and a wire harness for the FLIR View Pro R. The Plus T and FLIR thermal mapping sensor allows you to identify irrigation issues before crops suffer yield loss, inspect, detect problems with solar panels, identify building heat loss via roof. Another one of our packages that is very popular, especially with our agronomists, is the Plus M. That stands for multispectral. And like I said, agronomists, researchers, and other precision agricultural professionals can gain viable insight into the fertility of their crops with the Plus M. This payload features MicaSense Red Edge, a multispectral sensor, which allows you to monitor nutrients and moisture levels in your soil, identify and measure crop issues like disease, pest problems, weeds, and water stress, estimate yields, also characterize soil and vegetation cover, use data for predictive analysis, and your UAV flies over the field. Plus M captures with a 5-band spectral band. The data is processed in an indice tailored to specific agricultural applications. From the data, the user can gain deeper understanding of the conditions of the crops being analyzed. One of our newest payloads, it says coming soon, but it's actually sooner. It's now. In the next couple of weeks, we're actually offering it around the world. It's the MD Detector series, and the first of the MD Detector series is the CH4. CH4 stands for methane. So the newest, so this package detects methane gas, which is primarily used for finding gas leaks. This package is designed for professionals or companies responsible for inspecting gas, i.e. methane infrastructures. Examples are natural gas line surveys, tank inspections, gas well testing, landfill emission monitoring, and plant safety. The advantages are fast response and high sensitivity, detection at a distance, excellent selectivity for methane gas, it's lightweight, and it has a self-check during startup, meaning there's no calibration required for this sensor. This sensor is extremely easy to use because I use it. I'm a sales guy, so if that tells you anything. You can, with this package, we didn't just bolt a sensor underneath the MD4-1000 and call it a system. There's been a lot of work done to make this system work. You can view the data live in MD Cockpit software in real time during a flight, and the following information is available on that screen. A methane column density it's a calculation called parts per million times meters. Also gives you sensor status, and also plots the CH4 readings live. After the mission, you can view and export all the data collected using MD Detector Viewer app. You can download that data via Bluetooth as soon as the microdrone is landed. The data includes CH4 levels and GNSS position for every reading. The Viewer app plots these data points and color codes them into 3 different categories, which are customizable by the end user. You can also toggle between Google Imagery and Google Maps with the data overlaid, and you can export the data set to a CSV file to be analyzed in GIS software. I won't go through all the details of this, but it basically detects 1 to 50,000 parts per million times meters. That's an algorithm that I can only explain from what you can see there. It gives you 10 readings per second, and you have to fly within 100 feet of the ground. The package includes the Pergam LMM Gen 2 sensor, mount that integrates the sensor with the MD4 1000, an HD first-person view visible video camera to see exactly where the laser is pointing, a stabilized nadir mount supporting the sensor, HD video link for viewing what the sensor is looking at real time, and you can look at that on the 7-inch LCD monitor. So there's a little bit of, if you've been paying attention, there's a little bit of commonality across a couple of our packages. If you already own the Plus I, the inspection package, some of these things are already included. So pricing for this package varies depending on what you have. If you don't have a system at all, and then it's a little bit more. If you already have one of our systems, you know, we offer all sorts of different variations for it. Okay, so coming soon, and this is also coming, I think our first release for LiDAR, I'm hoping, and hopefully Dr. Mohammed won't try to punch me through the phone, but I'm hoping that we will be releasing something this winter in LiDAR. And one of the advantages is it penetrates tree foliage to give ground mapping data. It's fast for quick 3D modeling. Surface data has higher sample density, and it allows you to collect data at night. And we're going to combine that with a visual sensor to colorize the point cloud. The first one we're targeting for release, there's going to be several over the course of a year, but the first one we're going to release is the Regal VUX-1, which will go underneath the MD4 3000. Now back to you, Dr. Mohammed and Mustafa.
Thanks, Chuck. In the last couple of years, we learned from our products in the DG product line that photogrammetry is a great method of acquiring data, processing it, and turning data into information that helps the decision makers with their projects. However, photogrammetry has a limitation with producing elevations, ground elevations. And therefore, we started to look into the LiDAR solutions, as Chuck mentioned. And we are actually working on a range of products for LiDAR. LiDAR stands for light detection and ranging, and it's basically laser scanning. And what we have accomplished so far is that we replaced the DG solution cameras with laser scanners. And again, so you end up with a solution as opposed to just a drone. So the solution incorporates a drone, as well as the LiDAR sensor, as well as the necessary software for data acquisition and data processing, and then the people that developed all of the above. The mathematical concept is identical to the photogrammetry concept, except for that you don't have an image involved. So you're not actually reading one pixel at a time. You just have one vector from the drone all the way down to the ground, which is the range of the laser sensor pulse. What we have done is that we went through a detailed error budget, and this is a simplified version of it. And you can tell here that there are 4 verticals when it comes to errors contributing to the final mapping product on the ground. The georeferencing errors, the sensor errors, the calibration errors, and another group of factors affecting the final ground positioning accuracy. And we have gone through an extensive mathematical modeling and error budget analysis to understand every effect of those errors, so that eventually we know the contribution of each of the sensors, or the calibration methodology, or the georeferencing by GNSS inertial on the final mapping product positioning accuracy. And that is actually well embedded in the software slash hardware slash firmware of our solution. This is our workflow recipe. Basically, it's the similar workflow to the currently existing DG system for mission planning, data acquisition, data processing, and the final map production mode. So there's not much difference except for the accommodation of the laser scanner versus a camera in the solution. Some accuracy assessment results. We've done a project in Quebec in Canada, and that project has, as you can see, the logos at the bottom of that slide, the University of Sherbrooke in Quebec, and a number of other organizations. Basically, the objective of that project is to measure the snow depth in order to assess the effect of the depth of snow on the avalanches that happen up in the mountains in eastern Quebec. And traditionally, they have done this by digging 10 foot by 10 foot by 10 foot cubes. And they used to have surveyors going into those cubes and measure the snow depth using tapes, or even a little more sophisticated technology for measuring the snow depth. And they repeatedly done those cubes about 100 times over the mountain in different spots so that they could measure an average snow depth around the mountain area. And you could imagine when you dig a cube of 10 foot by 10 foot by 10 foot 100 times while it's still snowing, it was a fairly challenging from the logistical perspective and so on and so forth. In our case here, you can tell that all of the equipment needed to do the job was actually managed by a young lady. She's driven the whole group of equipment, and she's done the flights, and she processed the data while she was on site. And she's actually on the picture on the left-hand side here. The concept is fairly simple in our case. We're not actually measuring the snow depth physically or literally. What we've done is that we surveyed the area, including the mountains, in the winter time and in the summertime, and we just subtracted the digital elevation model between summer and winter, and that's how we ended up with the snow depth. A fairly simple approach, and that's exactly what we have accomplished here. We wanted to assess the level of accuracy that we ended up with. So in the lower right corner, there is, you can see that there is snow in the background, and then there is a big red target. That's a ground control point that we wanted to use for assessing our accuracies. And when we go through this slide, there's a table on the left-hand side showing the accuracy as an RMS. That table is actually written in French, so it's basically looking at the RMS root mean square error accuracy. And when Chuck actually moves through that slide, we will see some numbers here, like the repeatability and the RMS. The RMS here is 3 centimeters and 1.4 centimeters, which produces a very good level of repeatability between 2 different flights flown on 2 different days.
Okay, very exciting. Thank you, Dr. Mohammed. This is our DIKO pyramid. This is something that we preach. We're not out just to sell drones. Very often, customers come to me and ask me very technical questions about our airframes and this, how far and how long. And I always like to take a couple steps back, because it's not so much about the drone. It's about the data given to the decision maker, so the decision maker can make the right decision. So, starting at the bottom, you collect the data, and actually collecting data is very easy. So, but collecting quality data can be difficult, and that's the big differentiator with micro drones and all the others out there. Collecting quality data is very easy when you're doing it with a micro drone. You process the data into orthos or digital elevation models, which becomes information, right? So now you have information, and then the transformation of the information into knowledge requires experts. At each level, it builds on the previous. So basically what we're looking at here is garbage in, garbage out. If you're using if your system that you're using to collect data is not professional commercial grade, then every step after that is going to be multiply the effects of that. So I guess the key thing I want people to take away from this slide is, remember, the only thing the client is interested in is the answer. And the answer comes from the experts looking at they have the knowledge, they can read the information and make those decisions. So it starts with the proper airframe, the proper system. What should I consider when choosing a drone? Cost over time and ROI, obviously. Data accuracy. Not all results are created equal. Make sure you choose a professional system. Flight times with specific payloads, resistant to environmental changes or challenges. Technical support, quality engineering, the ability to swap out payloads, and obviously company stability. There's a lot of fly-by-night companies out there right now, and so you want to make sure that whoever you buy a system from, they're going to be around tomorrow. So that concludes our presentation today. We're going to allow questions to be submitted, and we can answer some this morning. And if we can't get to all the answers this morning, then we'll obviously reach out to you via email or phone call to answer your questions.
Yeah, thank you, Chuck. If anybody has any questions, please feel free to type them into the chat function right now. We'll be happy to answer them for you. Okay, one of the questions is it possible to get a copy of the slides from today's webinar? Absolutely. This presentation will be sent to you a few days after today. We'll send a link out to everybody that attended the webinar. So yes.
And I think is this webinar going to be replayable later too?
Yeah. So it will be hosted up on the Business Journal website at cnybj.com, and we will notify you of that as well. Do we have any other questions?
I have a question. Chuck, what is the next step if someone is on the call and they're thinking about making drones a part of their business? What should they do next to learn more, or to be walked through that pyramid of making sense out of it?
Well, that's a great question. And the first step would be my contact information's up there, my email. You can reach out to me regardless where you're located in the world. I can point you in the right direction, but I also can, I'll ask a few, usually first thing I do is ask a few questions about your business and what your challenges you are trying to do. That's really, from our standpoint, where the value is understanding our customers. It's not, here's a system, go ahead and buy this one and go up and do it. It's more about understanding what it is you're doing, what are the challenges, and then I can help you and my team can help you with the right solution. Because we offer many, as we've shown today, we've offered many different solutions.
And if I understand correctly, you're happy to help people regardless of whether it's ultimately going to result in a sale, because that's just part of the business right now. It's very exploratory, and there's been times where people have come to you for advice as a consultant, and you said, hey, for what you're looking at, there might be a different path, and you're able to guide them as well. So in other words, we're here at this stage of the industry to help consult, to understand what someone's challenges are, and if there's a fit, we'd love to sell you a solution. But in many cases, it's not the right match as well, and we send people in the right direction as well, correct?
Absolutely. Matter of fact, that happens a lot. And so to build off of what Mike's asking here, rather than be like a jack of all trades, master of none, we've decided our direction is mapping, surveying, structural inspection, and precision agriculture. That doesn't mean if you come to me with something else that, one, we can't help you, or two, I may say, we're not the best for that application. There's 1,000 different things you can do with a drone, and we're focusing on a certain area. But I would say more often than not, I'm helping people throughout the day they're not customers of ours yet, and they may never be a customer of ours, but it's something that I do all the time, is help and consult. I think that's probably one of the biggest strengths of Microdrones. We're not just building great systems. We're also a great partner, a great consulting company. We help.
And we have to be, because in this industry, we're not selling boxes that are on a shelf.
Sure.
It's really a solution sell, so we have to understand what they're doing.
Exactly.
What about, well, we're a global company, but we also, many of the people that are on the call here today are calling from upstate New York. By virtue of the fact that this is a CNY Business Journal presentation. Talk about demos in the demo process, that if someone is interested and they walk through some initial work with you over the phone, at some point we do a demo. Talk about how that works.
Sure. And actually, look, I'll start by saying we love to do demos, especially when they're local and I could drive there. But we get to the demo part of the conversation when we understand the customer's needs first, and what they're looking to do, and if we're the right fit. We don't mind going to the customer. It'll be me and a pilot, and with the payloads we need to do that demo. Or you can come to us. We have a couple different sites here in central New York that we fly at. One at the Griffith Airport, which is very exciting that we're able to fly there now. We have some other locations more remote. And usually, when we do a demo, it's not just, hey, let's go meet here and we're going to fly this drone. It's first of all, what do you want out of the demo? And most of the time for a mapping and surveying, they're going to want to see the data, obviously, afterwards. Even if the customer, we have a lot of very knowledgeable customers that want to process the data themselves, which is fine. Don't mind that at all. We'll hand them the data to do that. But we usually process the data as well and present them the data. So in case they process the data and don't get the same results, then we can dig into it and go, all right, your results say this, our results say that, and we can talk about how we did it and educate the customer, I guess.
All right. Well, remember, you can always connect with Chuck. He's left his email address up, so you can connect with him after this webinar as well. We do have a couple minutes more. If anybody else has any other questions, feel free to type them into the chat function. We're happy to answer them for you.
We also have Dr. Mostafa on the line still, so if you have some highly technical questions, we would love to try to stump Dr. Mostafa. I don't think it can be done.
Yeah, I challenge you. I challenge you to stump him.
All right. Well, thank you. Thank you to Chuck Dorgan and Dr. Mohammed Mustafa of Microdrones. Thank you to Visual Technologies for providing the technical support this morning. We will be sending out a survey with a link to the presentation in the next few days. We hope the content was informative, and thank you for joining us, and please enjoy the rest of your day.